Welcome back, everyone. This is our final meeting of the semester and of the year. And today we'll cover the next level up in the hierarchy of our understanding of our solar system, our planet, our solar system, galaxy, and universe. And that is the universe itself, the grandest scale, the field called cosmology, describing the cosmos in its entirety, what it is made of, how it is constructed, what it looks like, and how it has, as we now know, evolved over time. We'll touch on this topic briefly. Cosmology is, in some sense, merits a course fully on its own, but we'll kind of see the major developments, our major understanding, and the most important points of cosmology up to now and today. And I'll just give a sneak preview or a spoiler for what we'll slowly build up to for the rest of today's class. And that is the modern view of the evolution of the universe. Some of this might appear familiar to you from popular science knowledge or from any other source. The universe is understood today, or presumed today, to have begun with some Big Bang, some primordial explosion, which we do not understand fully. And we keep striving to extend our knowledge towards the Big Bang, understanding what drove it, what kind of physics was involved, and even if it happened at all, or if there was something else involved in the beginning. Following the Big Bang, the universe has been expanding. It's been expanding ever since. The first period of expansion was very fast. There was a period called inflation, where the universe expanded very, very rapidly for a short period of time to a very great extent. Following a roll down or a slowdown of the expansion, expanding slowly and slowly, basically up until the present day. And now, we'll touch on this in the end, the universe is seen to be re-expanding or re-accelerating. It's been expanding all the time, but the velocity of expansion is now accelerating again. So the universe kind of started with a Big Bang, expanded very fast, slowed its expansion, and is now starting to accelerate the expansion again. This expansion of the universe caused the density and temperature of various components of the universe to change throughout this time, which means different physics and later chemistry, even up to biology, were involved in different periods of the universe. So the universe began in a very hot, dense quantum state. Today, it is not in that state. Today, we see stars making up galaxies. Around those stars, we have planets with atoms and molecules and chemistry and all that. Much of that was impossible early on when the universe was too hot to sustain molecules. Before that, even atoms. Before that, even stable nuclei or stable nucleons, like protons and neutrons. And we'll discuss kind of this evolution of the universe through its various stages, inflation, as we mentioned, the dark ages, development of galaxies and planets from the Big Bang. Today, we estimate that to have been about 13.7 or 13.8 billion years ago. So that's today, the image today, but as I said, we'll understand how we know this and how this picture has evolved as recently as over the last couple of decades. So again, cosmology deals with the biggest questions, the ultimate questions, the questions of the universe in its entirety. And these questions of what is space, how much of it there is, how much time there has been for the universe, these questions have also been asked for basically as long as we have documented history, starting with naming some names starting from the Greek period, first asking whether the universe was even finite or infinite. Today we understand the universe to be infinite, but there were proponents of a finite universe. As recently as Kepler and Newton actually thought that the universe was not an infinite breadth of space and stars, but some finite system. building up since the time of Aristotle, posing that that what we see is basically all there is. In Aristotle's time, it was, of course, the Earth, the Sun, the planets around the Earth, and the celestial sphere of stars around it. People at the time of Greece even tried to calculate the volume of the entire universe, which today we realize is quite absurd. Together with the question of the extent of the universe came the question of what is at the center of the universe. Because if it is finite, then there's a clear geometrical meaning to where the center is, and that center shifted from the Earth in the geocentric models to the Sun in the Copernican revolution, and even before that. We saw 2 weeks ago that even as late as the 18th and 19th centuries, even as the beginning of the 20th century, people still considered, with observations, that our solar system was the center of the universe, that our Milky Way galaxy was the only one, and that we were at its center. And we already discussed how that was shown to be wrong, how we were shown to only occupy some outer region or some point on a spiral arm outside the center of the Milky Way, and the Milky Way itself, our galaxy, is only one in the local cluster, the Virgo cluster, which itself is only part of a larger supercluster, or the local cluster, then the Virgo supercluster, and Laniakea, higher and higher structures of clusters of galaxies. And so today we understand, except that there is no specific center to the universe. It's both infinite in space, and our point on it is not special in any way, and no other point is special in any way as well. There was also the question of whether the universe is the same everywhere, or is it different? Does it change from place to place? If you landed, if you fell asleep and woke up some unknown time later at a different point in the universe, could you tell where you were in the universe based on anything being seriously different, or would you just would it all look the same? That's the question of homogeneity. Closely related to the question of isotropy, does the universe look the same in every direction? All of these questions are the building blocks of modern cosmology, understanding how the universe is constructed in space and in different directions, and of course in time. Basically, maybe the most important question that we don't have a full, clear answer to. In the past, what was the beginning of the universe like? Was there even a beginning to the universe, or was it eternal going into the past? The Greek and the classical philosophers thought that the universe was always in existence, and it was stationary. It began an infinite time ago, and it will last for an infinite time into the future. Various creation myths, starting in Mesopotamia, or Greece, of course, of the monotheistic creation stories, which you can find from Genesis and onwards, describe a particular point in time, which is described as the beginning or the creation of the universe. Today, we relate this, the beginning, to this Big Bang, the moment in space and time in which space and time began. But as I said, we can only project backwards towards the Big Bang to a limited degree. We can't actually go all the way, because as the universe becomes denser and hotter going backwards in time, higher energy phenomena take place up to the point of quantum gravity effects, which we do not know and do not understand yet. So we don't actually know what happened in the beginning. But of course, it's one of the driving questions, maybe the most important driving question in this field, trying to understand how it all began. And the mirror question to that, how will it all end, and will it all end? What is the ultimate fate of the universe and everything in it, including, of course, ourselves? So the beginnings of the answers to these questions, which kind of were the foundations for the cartoon I showed in the previous slide, the expansion, the inflation, how the universe is understood today. The beginnings of these answers came only very recently in the 1920s, from the 1920s and onwards, when math and observations began to take precedence over philosophical considerations of what we think the universe should behave like. And because on the grandest scale, what governs galaxies and the universe in general is gravity, the modern answers are all basically related to or derived from general relativity, or at least we try to answer the questions in languages of general relativity, in the math of general relativity, and using observations of systems on a universal scale, systems like galaxies, and monitoring and watching galaxies, and as we will see later today, things beyond the galaxies that we can see, background radiation, cosmic microwave background, gravitational waves, and other questions, other tools for very, very far distance observations, the farthest that we can do on a cosmological scale. So 4 people are today credited with being the first ones to provide a solution to Einstein's equation of general relativity, describing the entire universe. Of course, it can't specifically describe anything, any particular galaxy or planet or matter accumulating in any particular point. That is greatly much too complicated for a single analytical solution to capture. But under basically the same simplifying assumptions, which are that the universe is generally the same in every direction and in every position, so homogeneity and isotropy. These 4 people independently derived the same metric written here in the middle, today called either the Robertson-Walker metric, which were the last 2 people to describe it, but the ones who popularized it, or in the full name, the Friedmann-Lemaitre Robertson-Walker metric for the 4 people who independently found it. Alexander Friedmann here on the right famously solved this equation quite quickly after Einstein published his theory of general relativity, only about 6 or 7 years later. Actually met Einstein, presented him with the solution, and Einstein who was a staunch believer in the stationarity of the universe. Recall from our discussions of general relativity that Einstein added a cosmological constant to make the universe stable and stationary, because he saw from the equations that without it, it would not be. So Einstein rejected Friedmann's result with the exquisite response that his math seems completely correct, but he understands nothing about physics. And today, of course, we know that it was actually Friedmann who was correct and Einstein who was wrong. The math in this case does describe the metric of the universe, and Einstein removed the cosmological constant, basically accounting for a universe which could be dynamic. Lemaitre was another interesting character here pictured on the left. Lemaitre was a Belgian Catholic priest, and he was the first one basically to understand that Einstein's equation implied a creation moment for the universe, that he understood that this metric, which can be characterized by this function R of t, basically the scale factor of the universe, would begin when that scale factor is 0. So when the entire universe is condensed in the past to a single point, which he called either the primordial atom, as in the single point from which the universe began, or the cosmic egg. Both of these names luckily did not catch on. His theory of a creation of the universe at a single moment in time did not catch. He was viewed as kind of a religious apologist trying to explain religious notions of creation to the scientists while not being truly interested in the science. Today, of course, we know that he was again right and the mainstream scientists were wrong. The universe, we can now project backwards in time and see that in fact the universe has been expanding and therefore did begin in some very, very dense point. And that explains a lot of the phenomena that we see today. Today, the name for that point beginning the universe is the Big Bang. I'm sure you've all heard of the term. The term was actually not coined by proponents of the theory, but they were coined by Fred Hoyle, an opponent of the theory. Fred Hoyle was a leading astronomer who did not believe in creation, in the Big Bang. And so to mock it, he called it, he said that some people believe the universe began with some big bang. And that name caught on, and today is the name of that beginning of the universe. Again, what this equation basically describes is that if you ignore for a moment this k parameter, which we will discuss later, then you see here in the parentheses basically just spherical coordinates, dr squared plus r squared d theta squared and sine squared theta d phi squared. Just your regular coordinates r, theta, and phi, spherical coordinates. That's for the spatial part, and just dt squared for the time part. So this is basically, in that sense, Minkowski flat spacetime, only in spherical coordinates. There are only two differences between this metric and the FLRW metric. The first is this R, capital R, which changes with time. Again, the scale factor. That means that if this function R, for example, grows in time, then things get stretched in time. That is, as time advances in its regular pace, space does not remain the same. If you want the cost in the metric, or the distance between 2 points who are spatially separated, grows relative to the time separation as the universe expands and kind of takes those 2 points, any 2 points, away from each other. That's if R is growing. If capital R is decreasing, then the universe is shrinking. And both of these solutions are possible under the Friedmann-Lemaitre-Robertson-Walker metric. It just depends on the content of the universe and the initial conditions of the universe. But this R captures expansion or contraction of the entire universe. This k parameter is another curvature parameter, the intrinsic curvature. And that, as you can see, comes only inside the spatial part. Basically, if k is 0, then again, this is just flat space, flat Euclidean space being stretched out in time. If k is either positive or negative, then that would create a universe whose spatial part is not flat, but rather the surface of either a closed sphere or an open infinite hyperboloid. So either positive or negative constant curvature, describing the different possibilities for the grandest scale curvature of the universe, flat, closed, or hyperbolic, spherical, hyperbolic, or flat. Okay, so these were the solutions, the mathematical solutions for Einstein's equation, attempting to describe the whole universe and predicting that it could contract or expand. As I said, these were completely rejected by scientists during the 1920s when they were proposed, the first ones, and they were only accepted in the 30s after Robertson and Walker presented them, when there was observational evidence to actually indicate an expansion of the universe. And we attribute this evidence to Hubble, Edwin Hubble, whom we mentioned already I think 2 weeks ago in describing finding other galaxies and measuring the distances to other galaxies, first and foremost, Andromeda galaxy, or the Andromeda Nebula, which was then accepted as understood to be the Andromeda galaxy. What Hubble did was measure the redshift coming from different galaxies relative to their distance from us. So redshift, as we said, indicates the velocity at which they propagate either towards or away from us. In the case of redshift, propagating away from us, which means that the light coming from the galaxy to us looks dimmer or redder, less energetic than it would have looked at the source. And you can translate that redshift in wavelength to a relative velocity at which the galaxy is moving away from us. And that's what Hubble did. And we see here his original 1929 paper with the important figure. Different points here represent different galaxies. And you can see the distance to the galaxy on the horizontal axis and the velocity equivalent or explaining the redshift on the vertical axis. And what you can see that Hubble found was that there was basically a linear or almost linear relation of increasing redshift with increasing distance. Of course, points don't always fall exactly on the same line. Things have random motions as well. But on the average, this effect is quite clear. You can see that the further a point is from our own galaxy, or the further a galaxy is from our own, the faster it seems to be moving away from us. Okay, that was kind of discovered earlier in the 1910s by Slipher and Campbell, but not yet understood in a systematic and convincing fashion. Hubble really gave this description of every galaxy expanding away from us or running away from us faster and faster the further away that it is. Is this result clear? Maybe the most important astronomical result of the 20th century, the galaxies running away from us. Any questions?
Yes, I think it's clear.
Okay. So I will say that in itself, this doesn't show that the universe is expanding. This just shows that from the Milky Way, every galaxy around us is escaping or running away from us, and that it's expanding away faster the further it is from us. But it's a very small step to come from here to an expansion of the universe. And the way to do that is, again, to adopt that Copernican principle, which says that we can't be special in any way. It's very unlikely that we are exactly at the center, the single point from which everyone else is running away in every direction. We have to assume that if we see every galaxy receding from us faster and faster the further it is away, then every observer in any galaxy in the universe should basically see the same picture. Any observer should see all the galaxies escaping away from him or her, which means that every two galaxies or every 2 points in the universe must be moving away from each other. And that's where the universal expansion comes from in Hubble's law, which is basically just relating, finding the slope of this line and saying how fast a galaxy is moving away from you, or how fast a point in the universe is moving away from you, based on how far away it already is, and saying that it's a linear relation. And that is Hubble's law. It says that the velocity is some constant, which Hubble called Hubble's constant. It's the slope of this line, times its distance from us, or from any other point. That's the expansion of the universe. So established in the late 1920s. And then, of course, people realized that this is exactly what is captured mathematically by the Friedmann-Lemaitre-Robertson-Walker metric. This factor R, capital R, would be the thing that's basically blowing up the universe, expanding the scale. Okay. Hubble's prediction of the expansion of the universe has an immediate repercussion. And that is that if the universe is expanding all the time, if you play the tape backwards, if you run things back to the beginning, you'll find that there was a beginning, because when things expand, if you play it backwards, things are contracting to a point. And if you know the velocity at which they're expanding, you can very quickly convert the units or inverse the calculation and find how long ago this happened, how old the universe is. So from this plot that Hubble presented in 1929, the slope of his line, you'd notice that the axes are kilometers per second and parsec, so velocity versus distance. And so the slope would be this velocity divided by distance. In this case, velocity calculated from the redshift divided by distance in megaparsecs. And this is kind of the standard units of Hubble's constant since then, kilometers per second, 2 megaparsecs. And he found a slope of about 530, which today we know is greatly over exaggerated, but that's the number that he found, 530 kilometers per second per megaparsec. These are funky units. They're kind of strange in that we have distance divided by time divided by distance. So in fact, you should be able to convert this Hubble's constant to units of 1 over time, or inverse time, simply by making sure that the megaparsecs and the kilometers are given in the same, on the same scale, in the same measure of kilometers. And this is carried out here. If you convert a megaparsec to kilometers, then a megaparsec is 1 million, so 10 to the 6 parsecs. Parsec is 3.26 light year. So a light year is 1 year in time times the velocity of light, 3 times 10 to the 5 kilometers per second. Convert, and then we get that we can kind of cancel out kilometers per second on the left and kilometers per second on the right. And we remain with 10 to the 6 times 3 times 10 to the 5 times 3. So about 10 to the minus 12, 1 over years, or 1 over 10 to the 12 years. That's converting the Hubble constant to time. And again, that means that if you have an expansion with a slope of 1 over 10 to the 12 years, then at any point, if you run it backwards to the origin, you will have hit the origin about 10 to the 12 years ago. So about a trillion years. And that was the first, yes, that would give you a trillion years. That's just the units though. We have this number 500 in Hubble's constant. If we include that in the calculation, then we divide the trillion years by 500 and we get about 2 billion years. And that was Hubble's estimate, or I should say, the estimation derived from Hubble's law and Hubble's constant for the age of the universe. The time ago when all of the universe, all of the galaxies emerged from the same point. I'm saying it's derived from Hubble's law, but not exactly Hubble's law, Hubble's estimate. Hubble didn't actually believe in this expansion. He also thought this was kind of too far out to be actually true, to actually describe the universe. He thought it was just indicating some measurement factor that he doesn't know how to account for. But other people built on this result and realized that it was a physical effect and it was indicating expansion of the universe. When you overlay it with the Robertson-Walker metric, then you realize that it has to be the correct answer, real expansion indicating a real age of the universe. This was an interesting estimate for several reasons. Some of them we already mentioned. We mentioned that the Lord Kelvin estimated the age of the Earth as a few tens of millions of years and the age of the sun as a few tens of millions of years. So this number was much too high for that. We said that Darwin and Smith both estimated from either biological evolution or geology considerations that the age of the Earth should be hundreds of millions or billions of years old. So that was kind of in the ballpark. But by this point, the 1920s, we already had radioactive dating of various rocks on the Earth. So carbon dating, as you saw in an earlier homework exercise, can't be trusted beyond a few tens of thousands of years. But uranium, potassium, and other radioactive substances have half-lives in the billions of years. And so those could be used for an estimation. And there were rocks on the Earth found to be as old as 3.4 billion years. So that's, of course, good for the biologists and the evolutionary theorists. It shows that the Earth was around for a long enough time for their effects to work out. But it was still a problem for the physicists and astronomers because there were rocks on the Earth which appeared to be older than the universe in its entirety by about a factor of 2. So there were still some problems and discussions and debates about this, again, explaining why Hubble didn't think that this was actually indicating an expansion or a finite age for the universe. Astronomers like Eddington proposed that the universe, in fact, expanded for 2 billion years, but that it didn't begin at that point, that it existed in some steady state, and at some point only then started expanding. Other more skeptic astronomers, like Fred Hoyle, which I mentioned, Bondi and Gold, said that the universe only appears to be expanding, but in fact, matter is always created and filling in the gaps, and the universe is gaining mass from somewhere, what's called steady state theory, maintaining that the universe appears to be expanding, but hasn't actually been that way forever. The solution for this debate, or this conundrum, was simply that Hubble's calculation was actually wrong. This plot, which he gave in 1929, which showed the distances to different galaxies, comparing them to their redshift, well, actually had the slope wrong because it had the distances wrong. And to understand that, we have to go all the way back to Hubble's kind of breakthrough, which we talked about 2 weeks ago in studying the Andromeda galaxy. If you remember, Hubble proved that Andromeda was a separate galaxy by measuring the distance to it. And he measured the distance using variable stars, Cepheid variables. So if you recall, Henrietta Swan-Leavitt in Harvard showed that Cepheid variable stars have a relation between their luminosity and their period. And if you calibrate that absolute luminosity to the period, if you then see a Cepheid variable star and you have the observed luminosity, compare that to the absolute luminosity, will give you a distance. So you measure the period, you infer the absolute luminosity, compare it to the measured luminosity, and you get the distance. And this is what Hubble did. He used her formula to measure the distance to multiple variable stars, Cepheid and others, in Andromeda, and compare it to the Milky Way, and find the distance. However, Hubble only knew one class of Cepheid variable stars. He didn't distinguish between the two families that we recognize today, the blue and red Cepheid variables. And this is what Walter Bade did. Walter Bade measured Cepheid variables as well, but he noticed that there was a distinct difference between the blue and the red stars. As we recall from the galaxy discussion, blue stars are typically younger, they appear on spiral arms. The red stars are typically older and even dead, and they will kind of appear in the older parts of the galaxy, or the part in the galaxy where stars are older, which is clusters outside the center and the actual center of the galaxy. So Bade distinguished between these two families of Cepheids, type 1 and type 2 Cepheid variables. And by doing that, he was able to recalibrate the period luminosity relation and realized that Hubble was analyzing one type of variables in Andromeda using the other family's distance calibration measure. And if he corrected for that, then what he got was that Andromeda was actually twice as far as Hubble had first estimated, which means that the slope of the line in Hubble's diagram plot should actually be half of what Hubble thought, because if you stretch the x-axis and double it, then you're cutting the slope by 1/2, and that doubles the projected age of the universe. So this kind of simple analysis of Cepheid variables in two families, which calibrated the distances, calibrated the slope, and then changed the age of the universe by a factor of 2, immediately helped everything fall into place. Because now the corrected Hubble estimate is 4 billion years, which is now older than the Earth. And now now there are no longer any contradictions. The Earth is very, very old enough for geology, old enough for biology, old enough for evolution. The solar system is very old. The universe is even older. And for the first time, when this was realized, all the pieces in the puzzle began to fall into place, and showing that this expansion of the universe can actually explain the time durations of processes that we see on the Earth itself. Hubble himself, to his death, did not accept this result. As we said, Hubble based his career and his prominence on measuring the distance to Andromeda and proving that it was a separate galaxy. So these young scientists showing that his very first claim to fame was actually wrong by a factor of 2 was a great hit to his pride, which he did not recover from, and which is a shame because his accomplishments are enormous. He proved that there were other galaxies and he proved the expansion of the universe. He just had a factor of 2 wrong. That's not so bad. But his measurements themselves were not the best. Henrietta Swope later joined him, and together they corrected the estimate of Hubble's constant H0 down to about 100 kilometers per second per megaparsec. So now this indicates a universe which is about 10 billion years old, even older than what was previously thought. And finally, in the late 50s, we kind of settled on an accepted value of Hubble's constant of about 75 kilometers per second per megaparsec, indicating an age of the universe of about 13.5 billion years. And as I said, this is already very close to what we believe today. We don't know the exact Hubble's constant today, but it's something around 70. Estimates vary from about 67 to 75, so definitely the correct ballpark. And accordingly, the age of the universe is about 13.7 to 14 billion years. That's basically the story of how we came to realize that the universe was expanding, how fast it has been expanding, and how old it is. Any questions?
Yes.
Yes.
I wanted to ask if there's any good estimation of the force making the universe expand, or any good theory explaining it by now, or is it still a huge mystery?
The expansion itself has an excellent theory explaining it. It's the theory of relativity. Einstein's theory of relativity, general relativity, has as a solution this Friedmann-Lemaitre-Robertson-Walker metric, which in some sense you can think of as saying, I guess in the Newtonian or the mechanical analog, that if you take galaxies and you throw them apart with some initial velocities, they'll move away from each other. Right? If you give some ball of matter some initial energy, it will expand. How fast it's expanding, or will it continue to expand, is a question of initial conditions. No physical theory, no general physical theory has a good explanation of initial conditions. For those, you actually have to ask deeper questions. But at least it's explaining that some expansion is completely plausible. You don't need a force to maintain it, right? This is kind of the difference you learn maybe in first-year mechanics. If you see a ball moving through vacuum, it will maintain inertially its velocity and direction. You don't need any new force or energy to give it. It will just continue. That's the law of inertia, Newton's first law, or Galileo's basically description that says that things in motion will want to continue in motion. It's true that the expectation when this theory was presented was that similarly to a mechanical system, if the initial conditions include some velocity, gravity will provide an opposing force, and gravity between the different galaxies and parts of the universe will pull it together and slow down the expansion. And that begs the question of how long will the universe keep expanding for, and what will be the end? Will it have enough kinetic energy in some sense to expand forever, or is it essentially a trapped system which will expand more and more slowly until finally it stops and then falls back? So the closed versus open universe, or the eternal expansion versus the imminent collapse, the opposite of the Big Bang. And we'll talk about that shortly when when we discuss the mechanical analogs or the non-relativistic analogs of cosmological expansion. Okay?
Thank you.
So I'll just conclude this first section with listing here modern measurements. These are the most, as of about a year and a half ago, these are the most current measurements or estimates of Hubble's constant coming from different methods of measurement. So Cepheid variables used for calibration, you can see up here in blue. It says, the top here says late universe, because these are measurements from our cosmic neighborhood. So they're done basically up to a few hundred megaparsecs or gigaparsecs away, so close to our own position in the universe, which indicates recent measurements because they're also close to us in time. This information propagates to us in the speed of light. So all these late measurements you can see from Cepheid variables, from Mira-type stars. We talked about Mira variables as well. Lensing masers, all these different estimates taking place in the late universe. And you can see that they basically revolve around this number of 72, 73 kilometers per second per megaparsec. Here on the right side, you see a few other types of measurements coming from the very far universe. So from basically background radiation, cosmic microwave background, measured from different types of missions, the Planck satellites, baryonic acoustic oscillations, different measurements applying to the faraway universe. And interestingly, being far away means that they're also far away in time. So in the earlier universe, these kind of congregate around a value of 67 or 68 kilometers per second per megaparsec. There is a 5 sigma or 4 sigma discrepancy between these early and late measurements. And this gap is considered still one of the most important open questions in cosmology. How is it that we can't even get a fair, consistent estimate of the most basic parameter, the expansion of the universe, 100 years after Hubble, agreeing between the early and the late universe? Obviously meaning that there's something we don't understand either about how we do these measurements or about how the early and late universe have been expanding. So cosmology is not a historical review of the early 20th century. It's still a very, very heated debate and ongoing field of research. Okay. I'll just summarize kind of this point that we mentioned before we go into the more mathy part of today's discussion, mechanical and then relativistic cosmology, that today cosmology is a field founded on what's called the Cosmological Principle, which in some sense is an expansion of the Copernican principle. It means that the universe is everywhere the same. It's homogeneous, everywhere the same, and it's isotropic. It's the same in every direction. Obviously, this principle breaks down if you sit at your table and look to your left or to your right and see someone who is not you. So those two directions are different and those two positions are different. But on a large enough scale, when you zoom out of all of the people and planets and solar systems and galaxies and clusters of galaxies, and you kind of see this cosmic web emerging, then the texture of the universe is the same everywhere. The details can be different, but the texture is homogeneous all across the universe. It has no center. It's infinite in every direction in space. However, it is not infinite in time. It has been expanding for about 13.7 billion years from a point which we call the Big Bang, although we don't understand it fully and don't know exactly what happened there. The universe is not stationary. Those ideas of Aristotle, Newton, Kepler, and even Einstein have been discarded. We see that the universe has been changing throughout its evolution, again, expanding to become thinner and cooler, and so allowing for different physical processes to emerge. And we still don't entirely know the future of the universe and the ultimate fate, and we'll talk more about what kind of data we're looking for to answer those questions. Okay, let's take a break now and resume at 1 o'clock to talk about mechanical or Newtonian cosmology. Any questions?
Can I come to your office maybe to ask the question? Floor 5?
Yes, you may. I'm not at my office. I'm in the Zoom room. But
yeah, okay, but same floor.
Okay. So this part of the class is a bit anachronistic in that Newton didn't do Newtonian cosmology. As we said, Newton quickly realized from his universal gravity that the universe was actually unstable and unstationary, because masses attract each other, and so they would have to collapse. But he reasoned that the structure of the universe and the creator of the universe would manage some initial conditions in some magical way that they would sustain themselves as a stationary universe. We know that, of course, to be wrong, but we can use Newtonian principles, or at least the Newtonian analogy, to understand the different models of what this expansion of the universe means, and how can it be that the universe can just expand, and what it means for the universe to be open or closed, and different types of models of whether this is an eternal or a finite expansion, whether there will be contraction and periods, and understand what the universe looks like on a grandest scale. Before we solve it in full GR, which we will do, but first understand at least the Newtonian analogy, or kind of the mechanics of the problem in the simplest possible terms. So how do we understand it? We understand the universe, or the expansion of the universe, by defining coordinates. As everything in physics, and especially in relativity, we want to discuss the coordinates of different points in space, and we can think of these coordinates as attached to galaxies, but we don't have to. They can be, these coordinates also exist where there are no galaxies. But we'll think of the universe, and I have here this balloon representing the universe with points on it. And the points represent the coordinate system, and we'll call them co-moving or fixed coordinates, because as the universe expands, the grid will expand. It will basically look like this. Okay, so now we see the points are farther apart than they were. Each galaxy basically moved away from any other galaxy, and the coordinate points have been moving along with it. Okay, we also see, by the way, that there is no center to this grid. Every 2 points were close to each other. The universe, mind you, is the surface of the balloon. There is no inside to the balloon in the cosmological analogy, just the points on the surface of the balloon. And every 2 points are now farther away from each other than they were before. If I let some air out, a contraction of the universe, now all the points are close to each other. And we can also see Hubble's law on this balloon, because we see, for example, 2 close points, they will only be expanding a little away from each other, while 2 far away points will be, of course, expanding faster. Okay, so here we have that the farther a point is from some other point, the fastest or the further it will be expanding in any given point in time. So this is our analogy for the expansion of the universe, and a coordinate grid on that universe, the surface of this balloon. Okay, how do we then quantify what I just demonstrated on the balloon? We describe each point on the balloon or in the universe as a product of some x, which is a fixed name for the coordinate, and the scale factor a of t, which previously was capital R, and often it's in cosmology, it's often called A, the scale factor. X doesn't change in time. That is, for a particular point, a particular galaxy, X is like a name label. It's going to remain the same. But the position relative to any other point will be changing because A, the scale factor, is growing in time. How does it grow? Well, it obeys Hubble's law. So the velocity, which is the derivative of R, we can think of as a derivative of A with respect to t, because again, X doesn't change. That's just a name. It's the scale factor that changes. And so we find that we have A dot instead of A. And if we want to re-quantify this in terms of the original coordinate, then we find that the velocity of a particular point in space is the derivative of the scale factor divided by the scale factor times the distance. And again, we call this the Hubble constant or the Hubble factor. If it changes, this expansion rate. And again, this gives us exactly the linear expansion. The larger R, so the larger the distance between two, say, galaxies is at a particular point in time, the faster they will be expanding away from each other by some universal factor h of t, some Hubble factor, which is the same in all of space. But of course, it amplifies distances the farther they are away from each other, this expansion rate. By the way, this also tells us why we only see this effect on a cosmological scale and not in our daily lives. Because as we saw, this age, if we reduce it to reasonable units, it comes out to be 1 over something like 20 billion years as this factor. It means that if you want to get some measurable velocity between you and, say, a star nearby, when you multiply 1 over 10 or 1 over 10 billion years by the distance, and the distance to stars in our galaxy is typically of the order of a few tens of thousands of light years, then this effect will be, okay, 10,000 years in distance divided by 10 billion years, about 1 in a million. So this effect is basically completely negligible, even on a galactic scale inside the galaxy. And of course, it's even more negligible if you look at close by stars, even more negligible if you look inside our own solar system, completely irrelevant if you do measurements in a laboratory or on the Earth between atomic systems or mechanical systems. It's just a scale that makes it completely irrelevant. Any other force in nature, gravity, electromagnetic forces, weak and strong and nuclear forces, will be immensely more relevant than this Hubble expansion. In fact, even the Andromeda galaxy, our closest significant neighbor, is actually approaching the Milky Way. As we said, we expect a merger with Andromeda in several billions or tens of billions of years, because we're gravitationally bound to each other, stronger than this Hubble expansion can overcome. This Hubble expansion really only becomes relevant on the greatest of scales, outside our own cluster of galaxies, on the scale of the entire cosmos. Okay, so those are just a few points on how we kind of understand this Hubble expansion, even in this mechanical formulation. Another thing this mechanical formulation gives us is a way to really compare it to gravity and bring gravity in the picture. How do we do that? Well, if we assume the cosmological principle, which is homogeneity, so the same density rho everywhere, and generally in cosmology, a subscript 0 indicates the present time, and without the subscript is any point in time. So if we look at some ball in the universe of radius x, then we find that the mass is just the volume of that ball, 4 pi over 3 x cubed, times the constant density, rho naught, if it's at the present time. mass has to be conserved. No mass is coming into the universe. So this has to be equal to the same product at any other point in time. So r cubed times rho of t. Bringing the scale factor, this shows us that the mass, which is a constant up to some radius, goes like the density of matter times the scale factor to the third in the cubic power. That means that as the universe expands, this scale factor grows. And if the mass is conserved, then the density has to go down. And this also is something we already mentioned. The expansion of the universe makes it thinner and thinner and also colder and colder. The density of the universe decreases and the matter density decreases like the third power of the scale factor. Okay. What is the force, the mechanical force that's in operation against the expanding universe? That's gravity. Gravity, which tells us that the second derivative, or the acceleration of the universe, is given by the gravitational pull backwards on the universe, which is minus gm of the same ball over r squared. And so we can plug in m here, rho x to the third. And if we kind of bring out the scale factor, because x is just a name and it's really the equation for a, the scale factor, that interests us, then we find that the second derivative, or the acceleration in the expansion factor, the scale factor, is given by minus 4 pi g over 3. That's just a constant bringing gravity, times rho times a. Right? We had a to the third from the volume. We're dividing by a squared from the distance. So we find that the acceleration of the scale factor is the negative. It's a deceleration given by the product of the density and the scale factor. This is an equation, a mechanical equation for a of t. The scale factor is a function of time. It depends on the density and on Newton's gravity constant g. Any questions thus far? Okay, so the next thing to do is to solve this equation. And this is a simple equation.
I have a question.
Yes.
We have this equation, but I mean, isn't rho of t also dependent of a?
Yes. Yes, rho goes like a to the minus 3. Exactly.
Okay.
But it's still a very simple equation to solve, right? Because it's a second order differential equation. In ordinary differential equation, there's only one variable. There's just derivatives in time. It's second order, but the only function here is a. In other words, it's just like the equations we know from mechanics, where you have x dot dot equals some function of x. And what we typically do in mechanics when we have those types of equations is we integrate once, or rather, if we have an equation for x double dot, we multiply it by x dot. So we have x dot times x double dot, and that's just the time derivative of x dot squared, or what's often called a kinetic energy term, velocity squared. It comes from multiplying by a dot and taking a single integral. On the right-hand side, we expect a potential energy term. And if our force, which is the right side, looks like some rho naught divided by a cubed, by a squared, because there's one a on top and two on the bottom, then we already know the potential energy form of this force. Because a force that goes like minus g over a over x squared is exactly Coulomb's law or Newton's law. The potential energy will be minus g over a, or over x, right? The potential energy of electricity, or the potential energy of gravity. And that's what this equation of energy conservation tells us. It tells us that the kinetic energy term, a dot squared, or the velocity squared in the scale factor, is equal to the potential given by G and rho naught divided by A. This is just the integral. Plus this constant, which we call minus kc squared. And this constant is the constant of integration, because when you do an integral, you never know where the zero is. You have to add an integration constant, and that's what we have here. So mechanically, we just solved the same equation as the one describing a mass, a density, a homogeneous density ball under its own gravity, expanding with some initial velocity and slowing down under its initial gravity. Right? This is exactly, again, the analogy of potential energy term, a kinetic energy term, and some integration constant. Here we put in, again, the rho of t, and so we get x squared. But again, these are just different names for the same expression. Potential energy, kinetic energy, and an integration constant, or the total energy in some sense. Right? If you move the potential energy to the same side as the kinetic energy, which is here on the left, whatever is on the right is just the total energy. And in this case, x is just a name, so this is some constant. And its sign will be determined by the sign of k. And so again, we follow the mechanical analogy, and we recall that a system with energy conservation and a given potential has three options. Either the total energy is positive, in which case the system is unbound. It has more kinetic energy than the potential well in which it is placed, so it will expand out forever. It will slow down forever, but it will expand forever. Or the total energy is negative, in which case the system is bound. It will expand, slowing down until it reaches velocity 0, and then it will fall back to the original position. That's a closed universe, a universe that started with a Big Bang, is expanding while slowing down. Eventually it will stop, reverse, and collapse back to a reverse Big Bang. Or the intermediate case where the total energy is precisely 0, which means that the universe will expand forever in a kind of parabolic orbit, never reaching infinity, never reaching velocity 0, but always slowing down in this marginal case between stopping and falling back or continuing on forever. So this marginal case is kind of the critical case for the universe. If the universe has more mass content than the critical density, it's too heavy for its current velocity of expansion, which means it will break and collapse. If it has less density, then gravity is not strong enough to break it, and it will expand forever. And so k equals 0 gives us this critical density of the universe called rho critical. From the equation, it comes out to be 3 Hubble's constant squared divided by 8 pi g, which is about 1.88 10 to the minus 29 grams per cubic centimeter. And you can see that this is actually a ridiculously low density. It's a very, very low density. Recall that there are 10 to the 23 atoms in a mole. So this is a very, very small number. It describes the density of less than 1 atom per cubic centimeter. The density in a galaxy is more than 1 atom per cubic centimeter. But this is even below that. So the universe, to expand forever, to avoid criticality, the universe can be doesn't need much mass to actually do this. This spurred a lot of debate and research in the 1980s and 90s, trying to measure the density of the universe and understand whether the universe is supercritical or subcritical. That is, whether we will expand forever or slow down and then reverse. This was the major cosmological question about 30 years ago, until the discoveries of dark energy kind of flipped the tables. Any question about the Newtonian analogy, or how we understand the various modes of expansion or contraction of the universe in this Newtonian estimation of mass, density, energy, velocities. Any questions so far? Okay. The universe, however, is not Newtonian. And we know that general relativity describes that the universe actually has curvature. So we can't just think of it as some infinite plane expanding. We can't, and we don't necessarily have the possibility of thinking of it like the surface of a balloon either. Right? A surface of a balloon is a very particular type of curvature, because while the surface is two-dimensional, it's housed, or it sits inside three-dimensional space. So it's easy for us to relate to. We can see it in our eyes. But it's important to remember that not every possible curved surface, it actually belongs in a higher non-curved surface. So the example of those surfaces which can be embedded in a higher dimension are given here. We have this grid, which we described before. It's a flat space, in this case, a flat plane, two-dimensional. And we can think of it as the expansion of the universe as any 2 or 3 galaxies on this flat plane moving away from each other. That's this left side, kind of a surface of the balloon, a plane that's expanding. Points get farther away from each other or closer to each other if it's a contraction. But a plane is just one option. It's the middle of the 3 options presented here in the middle on top. And it's a very special situation, a plane. We can also think of a sphere, which is not a plane. A sphere is closed. That is, parallel lines will generally intersect. There are no 2 lines on a spherical surface which will never hit each other. And it's a closed surface. Even as it expands, it remains closed. The opposite would be this hyperboloid, where parallel lines, or so-called parallel lines, actually always expand away from each other. And so we don't have the same notions of geometry as we did on a Euclidean plane. In all cases, we see that the galaxies will be moving away from each other at any point. So we have the same expansion everywhere. But it has a very great effect on whether the universe is closed or open. Because if parallel lines, if these galaxies expanding away from each other are actually on a sphere, then they might expand away until they curve back and hit each other. And this is, again, an effect that's not a Newtonian effect. This is an effect of the curvature of the universe. And these are still embedded spacetimes. In fact, these were the 3 constant curvature spacetimes. And these describe what we called earlier the parameter K in the Robertson-Walker metric. The constant K, which can be either positive, negative, or 0, will describe whether the constant curvature of spacetime is closed, flat, or open. So we have, in addition to the scale factor, which we discussed in the Newtonian analogy, the universe's curvature has a non-Newtonian element, which is the curvature itself, the constant curvature, which can be kind of ball-like, plane-like, or hyperboloid-like. If we plot the scale factor, solving the FLRW metric in these different cases, then we find that the universe can have positive curvature, which means it's like a ball, it will eventually fall back. No space curvature means that it will marginally expand forever with some power, or negative, which means that it will expand even faster. and we can calculate kind of the volume of the universe in these various cases, or at least in the case that it's a ball, that it's closed, then the ball has some radius, and so we have a finite volume for the universe. If it's flat or hyperbolic, then there is no volume and the universe is in fact infinite. That's the constant curvature in the case of possible embeddings. Some curved spaces cannot be embedded in higher dimensional flat spaces. And we have nice pictorial representations of these. The reason that they're pictorial and they're kind of optical illusions is because they can't actually be embedded in higher dimensions. You can't build a model like these Escher paintings on the left, where water flows down a stream, down a waterfall, down the stream, and comes back to where it started. This is something that's impossible to actually embed in a higher space, which leaves us kind of lacking a good visualization. We're left with these optical illusions, as opposed to the nicely embedded spaces where you can just put the space, the two-dimensional space, fold it in 3 dimensions. Sometimes you can't do these foldings, and we don't know whether our 3+1 dimensional universe can actually be folded in some sense into a 5th or higher dimension and actually fit. Einstein's relativity describes the universe as a curved spacetime, but it doesn't guarantee us that there's any higher dimension in which this curvature flattens out in some sense. And tying together relativistic curvatures and Einstein's equation of relativity with the Newtonian notions of cosmology and mass density finally brings us to relativistic cosmology, which is what we do today and what we actually study the universe with today, the various possibilities for a relativistic cosmology. And so what we do is combine Einstein's equation and the Friedmann metric and produce the Friedmann equations. The Friedmann equations will be the analogies in GR of the Newtonian mechanics, or the Newtonian cosmology. They will describe in some sense the matter density of the universe. They will describe in some sense the expansion of the universe, the Hubble parameter, the velocity of the universe, and they will describe the equivalent of the force on the universe, that is the acceleration or deceleration of the scale parameter. We'll see that they are similar to the Newtonian equations in one sense, but there are differences. And so those differences will be important. So our starting point is Einstein's equation, which by now I hope you all remember from the 2GR classes. We have this R mu nu, which is the geometry of the universe, the Riemann tensor, and the Ricci tensor and the Ricci scalar. We have possibly a cosmological constant, which is this number lambda times the metric G mu nu, which will be the Friedmann-Robertson-Walker metric. And on the right-hand side, we have kind of the crucial factor, T mu nu, which is the stress energy tensor of the universe. It describes what's in the universe, the so-called matter side or the content side. Unlike Newtonian mechanics, in GR, we actually have to talk about what that matter will be composed of. And it doesn't have to be what we call ordinary matter. It doesn't have to be just atoms. Atoms and molecules and even whole galaxies will just be one type of content or right-hand side in these equations. And in cosmology, because we assume that the universe is very, very sparse and that these interactions are very, very weak, all the regular matter that we know will be modeled as dust in cosmological terms. More accurately, we're going to describe this right-hand side, this T mu nu stress energy tensor content of the universe, as some perfect fluid, some ideal fluid, which has a fluid density rho and a pressure P. And we know in relativistic dynamics, hydrodynamics, that T mu nu is a combination of this matter density and pressure flowing with the velocity of the matter. So this u mu is the force velocity, relativistic. And we have this trace term of the pressure. So basically, it's the diagonal has some rho at the 0, 0 component, and P cancels out on the diagonal or to some degree. And we have this combination of density and pressure, and velocity, which will determine how the matter behaves as a fluid. As the universe itself is, as we said, homogeneous, it's filled with this fluid with some density and some pressure. That's still very generic. And to be more specific, we have to say what the relation is between the pressure and the density. Some equation of state relating pressure and density. So for now, we'll just call this equation, we'll just give a parameter called W. W will be the linear ratio between density and pressure of our ideal fluid. Without going into what these rho and P are at the moment, or what this W is at the moment, this is already enough to solve the equation. Because we now have the right-hand side, we can calculate the left-hand side. And we can find that similarly to the Newtonian analogy, the defining factor in this Hubble expansion, or if you want, the scale factor, this velocity of expansion of the universe, the kinetic term in the expansion, will be precisely this matter density rho. And again, we have 8 pi Newton's G divided by 3. We added a c squared to balance the units. But basically, there's a linear potential energy term in rho alongside the kinetic energy term, which is basically a dot squared. As before, we also have this integration constant K, which is the geometric curvature, which again, we're going to take to be either 0, 1, or -1 by normalizing the units, describing whether we're talking about the geometry of a sphere, a surface of a sphere, a flat plane, or some hyperboloid. And we'll possibly maintain that there could also be this cosmological constant term coming up in the integration. The interesting thing to notice here is that we have a term that's linear in rho, a term that goes like 1 over a squared, and a term that's just a constant, a cosmological constant term, has no a dependence. Okay, this gives us the energy equation, which is the first of the two Friedmann equations, and it looks exactly like the Newtonian one. Aside from this cosmological constant, exactly the same equation. The second Friedmann equation comes from derivative, or gives us the acceleration or deceleration, and it also looks a lot like the Newtonian analog if we, again, remove the cosmological constant and remove the pressure term. The Newtonian calculation that we did basically ignored pressure. Because we were talking about matter, we treated this matter as dust, and as we'll see, because dust has very negligible interactions, for dust, we will assume that this W is just 0. So there's no pressure. On a relativistic footing, we have to consider that not only matter is the source of gravity, energy can source gravity, photons can source gravity, anything can source gravity. So we can't ignore pressure anymore. And so we have this added term describing the second Friedmann equation. And if we combine these two equations, we can see that they're actually consistent with each other under the condition of continuity or conservation of matter, the flow of matter, which is that rho dot at any point, the amount by which the density decreases or increases anywhere in the universe, is equal to -3 times h. That is the Hubble expansion of the density and pressure at that point. So this is just some analog of the continuity equation which you might remember from electromechanics. Any questions about the first or second Friedmann equations? I see by this point in the semester.
Can you explain the second equation again?
Yes. So if we did just Newtonian gravity, we would have that the acceleration comes from the gravitational force. So it would always be negative. The force also always pulls things in. It will be proportional to Newton's constant G, and basically the amount of matter in our ball, right? So that's 4 pi over 3 times a cubed, the volume of the ball, times rho, the density of the ball. That was on the right-hand side as the mass pulling the ball back in. So other than substituting that rho grows like a cubed and then dividing by a moving to the right-hand side, to the left-hand side, we have here the first term on the right and the term on the left are the same as the Newtonian equation, which we saw here at the bottom. A double dot equals minus 4 pi g over 3 rho times a. So I just divided by a, and I'm getting basically the same equation. But the relativistic version, the second Friedmann equation, has 2 additional terms. One is the cosmological constant. So the cosmological constant itself can also be a source of gravity, either inwards or outwards, depending on the sign of the cosmological constant. That's carried directly from Einstein's equation, if it is there, if there's a cosmological constant. The second thing is the pressure. The pressure, which in the Newtonian case we took to be 0, because we took the matter to be non-interacting other than gravitationally, so it had no pressure, pressure was 0. In the relativistic case, even things like energy, like photons, exert pressure and provide a source in Einstein's equations. So we can't ignore it. In Einstein's equation, pressure also appears as a source for gravity, so it's an added term to the Newtonian version. Okay, so now if you have some content in your universe and it has not only mass density, but also pressure, the source for gravity will be both the mass density or the energy density and the pressure. Both of them will source gravity. So gravity in some sense will be stronger if the pressure is positive. That's a non-Newtonian effect. That comes from the equivalence in GR between mass, energy, and basically the fact that the stress energy tensor, which is the source of gravity in GR, includes pressure as well. Stresses and energies and pressures come in as sources on the right-hand side. Okay?
Okay.
Okay. So to solve this equation, we have to say what this omega, what this W is. What is the relation between density and pressure? And the first thing we'll get is if we look again at this conservation equation, which has both rho dot h and both rho, h, and p. If we put in our equation of state that p is w times rho, then we have a slightly simpler equation, because instead of rho plus p, we will have rho plus w rho, which means we can have the right-hand side is linear in rho, so we can divide by it, and we can isolate rho on the left-hand side. On the right-hand side, we have h, Hubble's parameter, which as we defined was just a dot over a, the relative rate of expansion of the scale factor. And so we get a separable equation, a differential equation on the left, a differential on the left, a differential on the right. Both of them are in a single variable. So we can integrate that immediately, because in between this -3, 1 plus W is a constant. The solution of this integral is that rho goes like some power of the scale factor. It goes like the scale factor to the power -3, 1 plus W. And we can test that this is correct by putting in the different possibilities for W. The first one is the one that we discussed already, the simplest one, just dust matter. Particles of regular matter, which have their mass, and if they're very, very far apart, they have no interaction, so they have no pressure on each other. So W is 0. That means that rho goes like 1 over A cubed. And this is exactly what we had in the Newtonian case. We said that if the ball expands by some factor A, the volume grows by A cubed, which means the density decreases by A cubed because the energy, the mass has to be conserved. So if the volume grows by some factor, the density decreases by the exact same factor. Okay, that's the simple case. Radiation is a more interesting case. This is the non-Newtonian case. This is relativistic. Some of you might have already seen in courses in thermodynamics or statistical mechanics, maybe even earlier in this course when we talked about radiation pressure in stars, that this factor W for photons, for radiation, is 1/3. The pressure is 1/3 the energy density of a radiation field, of a photon, a gas of photons, if you will. What this means is that this exponent, -3 times 1 plus 1/3, becomes -4. So rho actually decreases like the 4th power of the scale factor instead of the third power. How do we understand this? How can the density decrease more than the expansion of the volume? Okay, here's a thinker. Any ideas? So in the case of mass, if you have a certain number of atoms of hydrogen, for example, and you double the length scale, so you multiply the volume by 8, the same number of hydrogen atoms now occupies 8 times as much volume.
Maybe they can't occupy the new volume, the photons, the radiation.
Again, so exactly, so the hydrogen atoms, their density will go down by a factor of 8. The same will happen for photons. If you have now a certain number of photons in a ball, if you double the scale factor, you multiply the volume by 8, the density of photons reduces by a factor of 8, of A cubed. But the energy of a photon is not constant because it's not just the mass of a hydrogen atom. The energy of a photon is proportional to its frequency, which is 1 over the wavelength. If you double the scale factor, if you stretch space by a factor of 2, then you stretch the wavelength by a factor of 2, so you halve the energy. You cut the energy by half. So A to the 3rd comes from the volume increasing, and another factor of A comes from the redshift, from stretching the photons and causing each photon to lose half of its energy, or factor A of its energy.
Can you explain the difference between the redshift and the wavelength?
Exactly. We are artificially redshifting the photon by stretching its wavelength cosmologically.
No, I mean redshift. One redshift. I mean one factor I can understand where it comes from. When we say, for example, now the same wavelength, but the distance is now larger because of the expansion, so it decreases the energy. But what about the second one? I don't understand. Then where this comes from?
One of them is volume. 3 factors of A come from the volume.
Ah, okay, okay.
It's the same 1 over a to the third comes from the volume increasing, density decreasing, number density decreasing. The fourth factor A comes from each photon losing part of its energy because it's being stretched and redshifted.
Okay.
So this is the first case we saw where this cosmological expansion actually has a clear physical result. It's not just rescaling everything, because different physical components scale differently with this expansion. Matter loses density by a to the third. Photons, radiation, lose by a factor of a to the fourth. Also interesting is vacuum energy. Vacuum energy has W of -1 because it's just vacuum. It doesn't depend on density. So it doesn't depend on A at all. What this means is, if we look at the universe expanding, at very early times, when T was very, very small and the scale factor was very small, when the universe was close to a single point, we can ignore K, which has the worst dependence on the scale factor. But we find that when the universe was very, very small, it was radiation dominated. Because if we take the radiation density in the universe now and reverse the clock by 14 billion years, reducing A to 0, radiation pressure will grow like A to the fourth. While matter density, which is what we see, like galaxies and stuff like that, will only grow like A to the third. So eventually, radiation will win out over matter, and we find that the early universe, the pressure and the density and the governing content density of the universe was radiation and not matter. Now it's matter. Now matter is the most prominent density in the universe. Back then, close to the Big Bang, it was energy that won out. And we can see this from the Friedmann equation that if you then take this alpha, the relevant A of whichever, if you want to expand your scale factor in time by this parameter alpha, or understand the polynomial behavior, you find that it depends on the relevant density content, or the dominant energy content at the universe at the time, where radiation and matter behave differently. So they provide a different type of slowdown or of push to the expansion of the universe. This is the first example we have of what we saw earlier in the epochs of the universe, that the universe can actually switch between expansion mechanisms, between the radiation-dominated universe and the matter-dominated universe. And as we go back in time, the universe becomes not only hotter and denser and smaller, it also becomes different. It's governed by a different type of physical processes and different types of expansion processes. Okay, let's take a break again until 2 o'clock and then talk about the matter-dominated universe. So I'm pausing the recording. Okay, we are back. So as we said, we solve the Friedmann equation, which is basically the Einstein's equation under ideal fluids matter content or stress energy content. And then it becomes crucial to distinguish between which type of content we are describing. And the easiest case, the dust case, the matter case, this is closest to the Newtonian case. And we find results which are, not surprisingly, not very different from the Newtonian. The technicalities are a bit different, but the equation essentially gives us similar behavior. So dust means that there is no pressure, so P and W are 0, which means, as we said, that we have a constant, which is the density in some sense, or the amount of co-moving matter, rho A cubed. The first Friedmann equation is then identical to the Newtonian equation, at least when there's no cosmological constant. And we talk about matter-dominated or radiation-dominated or any type of content dominating the universe, that typically means we're going to just take one and ignore all the rest. So in this case, we're ignoring the cosmological constant, ignoring whatever radiation there is, because it diminished much stronger than the dust matter. So we're left with basically exactly the Newtonian equation. It's typically common to replace the time coordinate t with what's called co-moving time eta, just by switching the variable of the equation from t to eta using this 1 over a. So kind of bringing the scale factor into the variable. We switch all these dot variables with respect to t with prime variables with respect to eta. That gives us a simpler equation, which is the scale factor derived, or the velocity of the scale factor squared, the kinetic term, is just given by this simple difference between two terms. One is linear and one is squared. We can solve this depending on the three different possibilities for k, 1, 0, or -1, which again is a sphere-like or closed universe, flat universe, or open universe. And we find, not surprisingly, similar to the Newtonian case, for the closed universe, we have the scale factor basically behaves like a cosine or like a trigonometric function. It rises in expansion until it reaches some end, some peak, and falls back on itself, collapsing back to a point, while the hyperbolic case expands infinitely with the scale factor growing linearly in time. And the intermediate case, the marginal case, has the scale factor growing like t to the 2/3 power. So there's a difference in the polynomial of these expansions. And these are the three options of a dust or matter-dominated universe, basically exactly like the Newtonian case, the three Newtonian cases.
Can I ask a question?
Yes.
About the co-moving time coordinate. I didn't really understand where it came from. And another question is in the equation in the bottom left. For example, the scale factor is shown in terms of eta, the co-moving time coordinate, and not and then t is also the. So if I want to get a as in terms of t, I need to isolate the t from the right equation and input it in the left equation.
Exactly. You can see that in the simplest case, maybe here in the flat universe. You see that the scale factor a goes like eta squared, t goes like eta cubed. So take the third root of the right equation. You'll have that eta goes like t to the third. Substitute that in the left equation, you'll get that a goes like eta squared, which is t to the third root squared. And that's exactly this scale factor goes like t to the 2/3 that you have on the right. It's exactly a problem of using this intermediate variable. And the reason we use this intermediate variable is just because it makes the equations a bit simpler. So it's difficult if you want to solve a differential equation, for example, numerically, if you have this a in the denominator, because a starts off as 0. You don't want to divide by 0. Singularities are not fun. So we just kind of absorb that singularity, the 1 over a, into our new coordinate. And now, in terms of eta, this second equation, a prime squared, is completely solvable, right? In terms of eta, because it has a and a squared. You can put 0 anywhere you want. There's no singularities. You can just solve it fully, and then go back to the original variable t.
So eta is another variable we made to help us solve the differential equation.
Exactly. It's co-moving time. It's kind of time normalized by the scale factor. That's exactly what this transformation means. And it's easier to solve the equations, a lot of cosmological equations, if you just put in a, combine it with the time coordinates for this new time coordinate eta. So that's co-moving time.
Okay, thank you.
Radiation-dominated universe is very similar. We just replaced W instead of 0, it's 1/3. And so rho a to the 4th is now the constant that's being preserved. The energy content in a ball, again, now depends on a to the 4th power and not the 3rd power. So in Friedman's equation, it's exactly as it was before, but instead of a single a at the bottom, C1 over a, we now have C2 over a squared. So the equation is slightly more complicated, but we can now solve this analytically directly, and we find that the solution here is a equals the square root of this complicated constant, which we don't really care about, times the linear function in t minus kc squared t squared. So this is even easier in the radiation-dominated case than the matter-dominated case. And we can see that the 3 different options here for k equals 1, 0, or -1, appearing on the right, look very similar to the matter-dominated case. So there's radiation-dominated on the right, matter-dominated on the left, dust-dominated on the left, but they're only qualitatively the same. They're not exactly the same. In the middle, we see them on top of each other. And we see that in every single case, the radiation-dominated ones kind of expand higher and faster. So here, the upper blue, the upper red, and the upper green are the radiation-dominated, and the lower 3 lines copied from the left are the matter-dominated. Maybe a more interesting way to think of this is that while all these, the universe might start as radiation-dominated, because when it's hotter and denser, A is smaller, and so rho a to the 4th wins out. That is, before radiation was stretched enough to lose dominance, we see that the universe expanded kind of fast, but then when radiation drops below the density of matter, it will switch to one of these matter-dominated expansions. So even the velocity or the mode of expansion will change during the expansion because of these different epochs of the universe taking over from one another. Okay, the last is the vacuum-dominated universe. The vacuum has a constant density. The cosmological constant is constant, and it doesn't depend on A, which means that as the universe expands and A grows, both matter and radiation will eventually drop below the density of the cosmological constant if there is a cosmological constant. So in the very far future, we expect this to be the dominant factor, this vacuum-dominated universe. And the case is here, the solution here, we see that there is no dependence on A in the matter case. And so while before we had some sines or cosines, now we have these hyperbolic functions, hyperbolic trigonometric functions, basically all growing exponentially in the far future. Okay, so in this case, if we have a positive cosmological constant, that means the universe will be expanding forever. While if there's a negative cosmological constant, the universe is closed and we're back to the cosine case. And if a cosmological constant is 0, the only way to satisfy that is when k is also 0, and we're actually talking about a flat universe. So a universe with no cosmological constant and nothing else to provide any content will be flat. Today, we again begin to think that there is a cosmological constant, that there is negative energy density, and that the universe will in fact be expanding forever. And if you recall from the beginning of the talk, of the lecture, this reacceleration here going up again is what we think to be the universe going back into an expansionary phase, an accelerating expansionary phase. So we were decelerating and now we're going back into accelerating. And the reason for this is that all the studies that I talked about 30 years ago, trying to measure how much the universe's expansion is slowing down, in fact showed that the universe was not slowing down, that the universe is now measured to be accelerating in its expansion, and that's what we call dark energy, and that's what we think will determine the future of the universe from now on. An important point to note about cosmological distances while we're on this scale factor is that just as different content terms in the universe, different rho densities, do not scale the same way with the expansion of the universe, different distances also scale differently with the expansion of the universe. And the easiest way to see this is that if you look at the two different possible measurements of distance, one of them will be angular distance, which is how we started off in astronomy, defining the parsec and defining measurements and distances to distant stars. And the second will be luminosity distance. In the near universe, in our local vicinity, we assume them to be the same, but they're in fact not if the scale factor behaves differently. So angular distance is defined, if you recall, by measuring the distance across the sky, so some angle, multiplied by the distance to that point. So it's a ratio, it's really given by a ratio of two distances, an angle and the distance. However, luminosity distance is calculated differently. Luminosity distance is calculated if you take all the energy coming out of an object. Imagine that the flux is distributed over a sphere of radius d squared, and then knowing the luminosity, dividing by d squared will give you the distance. So you have two measurements here. You have the ratio of two distances versus the spherical area of a distance squared. If distance changes with distance, these two functions will behave differently. They won't agree anymore. They'll be different from each other. So it's important to distinguish between, for example, this angular distance and the luminosity distance. And that means that distance in terms of parsecs is not always well defined or not the best parameter to use when you're talking about different astrophysical phenomena on cosmological scales. And the parameter that we like to use is the redshift, because redshift is well defined. Redshift is saying, I see a photon here, I know where the photon came from, I know the Hubble expansion, I can integrate back what color it had or how much energy that particular photon had when it exited the source. So we define this parameter z for the redshift, when 1 over z, 1 plus z is exactly the ratio between the observed wavelength of a photon to the emitted wavelength of the same photon. And that's exactly this parameter a. So a goes like, or 1 over a goes like 1 plus z. What this means is that when you're looking at the very near vicinity, a is expected to be very close to a0. And so 1 plus z is very close to 1. Z is very small. Z equals 0 is basically the here and now. And z grows the deeper away you look into the history of the universe, measuring the redshift. And it directly gives you the ratio between wavelengths and energies. And for example, you can then understand that the difference or the relation between this angular, this luminosity distance to the angular distance is the redshift factor squared. So you have to, so again, when you're close by, z is very small, they're almost identical. When you're looking very, very deep into the universe, z can be quite large. So you have to remember exactly how large it is. Theoretically, at the Big Bang, z is infinite. Although, of course, we can't actually probe that far back in z. So we would like to look very far back in z, but we can't look infinitely far back. Which brings us to the most, yes.
we said that Z is related to the universe expansion rate, right?
Yes.
So does it mean that Z is also a factor of time? So
Yes, of course. If you look farther and farther into space, you're also looking farther and farther back in time, which also means higher and higher in redshift. And these things on a cosmological scales become equivalent. How far ago in time it was, how far away in space it was, and how much bluer it was, or how much red it is by the time it gets to us, the redshift. And these are basically different measurements or different names to the same measurement of things being very far distant and far back away. Redshift, though, because redshift Z is almost independent of the cosmological model, you can probe it directly by comparing photons. And because most of the phenomena that we know from physics and chemistry, we can attribute to energy scales, it becomes much more convenient to discuss things in terms of Z. Because you can say at what Z some physical process happened, and you don't need to know the exact evolution or expansion of the universe or content of the universe all the way there. If you want to relate it to distance, then you do. You need to integrate over A of t or over A of z. But if you just want to discuss some process, you don't need to know everything that happened in between. You can just talk about something that happened at a z of, for example, as we will immediately see, at a z of 1,100, a z of 1,100, a very important z in the history of the universe. Okay, so in a lot of popular science articles, people will say this happened such and such billions of years ago. But in physical papers, people will usually discuss at what redshift it happened, because it's the more stable and the more precise notion is to discuss the relevant physics at a particular redshift. And maybe the most prime and important example of this is the case of the cosmological microwave background radiation, the cosmic microwave background, the CMB, in Hebrew, Chinat Hareka Akosmit. An amazing contribution and discovery in cosmology, maybe the definite proof of the Big Bang, or considered the best proof of the Big Bang that we have, a foundation in cosmology. And the story goes as such. So the universe, as we said, is expanding. And as it expands, it cools. It becomes less and less dense, more and more thin, and more cold. That means that if you go backwards in time, it was hotter and hotter. At some point in the past, you expected the average temperature of radiation of the universe, of the background in the universe, to be hot enough to participate in various physical processes. At that point, particles were created, photons were created, and they kept sweeping through the universe, which was getting colder and colder, too cold for these processes to continue. That means that in some sense, we still have in the universe photons created back when it was hot, and we still should be able to find this picture of what the universe looked like a long time ago when it was a lot hotter. So this kind of basic prediction was given by George Gamow in the 1940s. We remember Gamow from the Gamow peak in explaining the nuclear burning and nuclear penetration in the quantum tunneling to produce energy in stars. The same Gamow gave this prediction that there should be some background radiation in the universe, a remnant in the proof of the Big Bang. And it should be quite cold today. No one knew exactly how much, but the prediction was somewhere around microwave. He gave this prediction in the 40s, and some groups were looking for it. The group that actually found it was one that was not looking for it. As often happens, it was a pair of engineers and scientists working for a private company, for Bell Laboratories in the United States. And they were developing satellite communications, and they wanted to have an estimate of the background, of the radio background, in order to be able to better plan for their satellites. And what they did was measure at a wavelength of 7 centimeters, so kind of edge of the radio frequency, towards the microwave. And they found background noise. And what you often do when you want to develop a communication system and you estimate the background is you want to characterize what comes where and which directions are the best directions to transmit and receive and to put your satellites to minimize the noise. But they were getting this background noise from everywhere. And this is their original equipment that they used in 1965. And here we see the image that they had, basically this green blob covering all the sky. The middle, of course, is the plane of the galaxy. That's always noisy in all wavelengths. A lot of things happen on the galactic plane. But off of the galactic plane, all of the sky was noisy in the same 7 centimeter wavelength, and basically to the same degree. There were more and more Earth measurements up to the 1990s, reducing the wavelength all the way down to about 1 centimeter. You cannot measure microwave from the ground below 1 centimeter because the atmosphere absorbs it. So there was a problem and there was a limit on the technology that could be done. But even those measurements between 7 and 1 centimeters done from the Earth already showed that the distribution of energy by wavelength fit a black body spectrum, suggesting a temperature of about 3 degrees Kelvin, which fits a wavelength of about 2 millimeters. I'm going to correct this sentence here to English for those who don't read. It says fits a wavelength of about 2 millimeters. So by 1990, they had about 25 years of observations showing that there was a suggestive background radiation all across the sky. And it was aiming towards a peak at about 2 millimeters, fitting a temperature of 3 Kelvin. And the solution that they found to this puzzle was to build a satellite, the COBE satellite, designed to fly outside the atmosphere and measure radiation below 1 centimeter towards this 2 centimeter peak to really characterize what this was. And that gave the map here on the right. This is the COBE satellite from 1992 and the image of the sky in those wavelengths, in microwave. Again, of course, the galaxy itself is very, very prominent in the galactic plane. And we see maybe more purple on the right than on the left. We'll talk about this dipole. But basically, they confirmed that this radiation was coming from everywhere in the sky. So the sky was outside the Earth. The sky around us was full in every direction in this microwave radiation. Okay, so the analysis of this radiation, first of all, wanted to discard the most prominent noisy features. If you're looking to see the background, then the first thing you want to do is avoid anything in the foreground. That is identifying known sources of radiation and discard them. So the first thing was this dipole, this preference of one direction towards the other. This is obviously non-isotopic. So by the cosmological principle, it's non-cosmological. We understand this as kind of motion of our own solar system relative to the background. And you can see it here. That's why it's more purple bluish on the top right than on the bottom left. And if you kind of smooth the colors and average out the dipole moment of the radiation, then this is what you get. And you can subtract that away from your data. And then you're left with something here on the right, which now you see no longer has a preferred direction. We subtracted the preferred direction, the dipole. Still prominent is the galactic plane, but we know that. We know our galaxy, so we can calculate the profile of the spectrum in the galactic plane. It's not thermal, so you can kind of just give a function describing it, subtract that from the data, and then you're left with stage 3, what's really just the cosmic background, removing the solar system, removing the galaxy. You're only left with what's outside. And this, as you can see, is very, very regular. Actually, the differences here are amplified. It's a lot smoother than it looks here. The fluctuations are only about 10 to the minus 5. So it's a very, very smooth spectrum from every direction in the sky. And it fits a thermal spectrum of a black body at about 2.73 Kelvin. You can see it on the right here, the original COBE data on top of an idealized black body spectrum. And I should say that the error measurements here on the graph are actually amplified. The plus signs are about 1,000 or 10,000 times larger than the actual uncertainty in the data. You wouldn't see the error bars on top of the width of the line if they used the actual correct size of errors. This is considered to this day the best, most accurate black body source ever measured by man. It's a perfect black body spectrum like the ones you see in Introduction to Quantum Mechanics, a perfect spectrum coming from every direction in the sky, perfect black body. This is the cosmic microwave background from 1992 from the COBE data, which, by the way, is available. If anyone is interested, you can still find it and use it. Further satellites in the 2000s, WMAP and Planck, were launched every decade to refine the measurements, to get more and more spatial and angular resolution in this, in measuring this background radiation. You can see WMAP improving on COBE, and you can see Planck improving on that. And if you see here, kind of characteristic parameters, COBE had an angular resolution of about 7 degrees. WMAP improved that to ½ a degree, and Planck to 0.16 of a degree, so 15 times more sensitive than COBE. And we see now more and more features in this cosmic microwave background, all confirming the black body spectrum coming from everywhere in the sky. So as we said, where does this come from? It comes exactly from this history of the universe, and from the history of the universe successively switching between different types of content, of temperatures, and of allowed processes. So when the universe was very, very young and very, very hot, above about 3,000 degrees Kelvin, all hydrogen atoms were ionized to plasma. So there were no stable atoms, just plasma, protons and electrons running around freely. That means that photons couldn't propagate very far because, as you know, Compton scattering is an effective process. Photons scattering off of free electrons, exchanging energy with the electrons. So you could say that the universe was opaque, was optically thick. It wouldn't let light through. The universe was, in that sense, dark because photons would interact with electrons all the time and couldn't get through. That changed below 3,000 Kelvin. When the universe got colder, hydrogen atoms could recombine, or actually combine for the first time, and become stable hydrogen atoms. A stable hydrogen atom is terrible at blocking light because it's neutral, so it doesn't interact directly with the photon, and the photon can only cause an electron to jump between energy levels if it fits the correct Balmer series, Lyman series, Paschen series, all of those spectral series lines that you remember from quantum mechanics. That means that as the universe got colder than 3,000 Kelvin, it became transparent to photons propagating. So we call that kind of the last scattering surface, the last time that photons and electrons were in close equilibrium. Again, it means that above 3,000 Kelvin, before 3,000 Kelvin, photons were constantly interacting with electrons. So they were in thermodynamic equilibrium. There was an equilibrium of energy between photons and electrons. If a photon got too energetic, it would hit an electron and give away its energy. If a photon had too little energy, it would hit an electron and gain some energy from the faster electron. Energy transferring on average from the more energetic objects to the less energetic. After this separation, the recombination of hydrogen atoms, which means separation of matter from radiation, there's no longer equilibrium because now photons can propagate freely, which means these photons are propagating freely through all of the universe. The universe in its entirety becomes transparent to photons going through, which means we can still see today photons emitted at the last interaction that they had with electrons when the universe was about 3000 Kelvin. Today, the microwave background radiation is at 2.73 Kelvin. Last scattering occurred at 3000 Kelvin. So an easy calculation of the redshift tells us that the universe was 1100 times hotter then than it is now. And in fact, the radiation that we see as a microwave background is just the remnant of an equilibrium thermal distribution, perfect black body at 3000 Kelvin when the universe was at a redshift of 1100. So 1100 times hotter on average than it is today. And if you introduce the cosmological model, this brings you back to almost about 400,000 years after the Big Bang. So when the universe was about 1/3 of a million years old, very, very young, was the last time that these photons were in equilibrium with free electrons. And this is the radiation that we see today. We see the cosmic microwave background as the remnant, the cooling down remnant of this last scattering surface when the universe was 380,000 years old at a redshift of 1100. Any questions?
Yes. I think I have a question, but I can't. אני לא מצליח לנסח את זה לעצמי.
Okay, you can try.
So you said that the photons and the electrons were in equilibrium.
Yes.
But equilibrium means, let's say, energetic equilibrium, right? But the energy is transferred by the photons between the electrons. So how can you say that the energy that is the photons themselves is in equilibrium between these two?
So you can think of, taking some cold milk and pouring it into hot coffee. Very quickly, you will have a homogeneous compound where the milk and the coffee are at the same temperature, some equilibrium. How does this happen? The hot coffee particles, or the hot water, ignore the coffee, the hot water particles, whenever they hit a cold milk particle, on average, the hot particle will give energy to the cold one, the fast one to the cold one, to the slow one. Right? Energy typically doesn't, something fast doesn't hit something slow and get faster, most often. So it doesn't happen at once. You have to stir, you have to wait a little while for the coffee to thermalize. But when it does, you have a mixture of milk and water at the same temperature. The same happens for any mixture of two gases. If you give them enough time and enough, that is, if they interact strongly enough over enough time to thermalize. For example, if you have a gas of electrons and a gas of photons, and if they can interact strongly with each other, and photons do interact with free electrons in Compton scattering and inverse Compton scattering, if you give them enough time, they will thermalize. They will, on average, have the same amount of energy per particle, or more accurately, per degree of freedom.
So they were moving at about the same speed at that time. That's what we call it.
Not at all the same speed. Photons were moving at the speed of light. but every degree of freedom had on average the same energy. If you want, it's some version of the equipartition theorem from thermodynamics or statistical mechanics. If you let all the degrees of freedoms of all the photons and all the electrons interact with each other freely and intensely for long enough, eventually you'll have equipartition. You'll have equal amounts of energy per degree of freedom, no matter what population you have. You'd also have equipartition, by the way, between the electrons and the protons, which of course means that the protons will be slower than the electrons because they're more massive, but the kinetic energies per degree of freedom will be equal. Again, equilibrium. Different populations, if you allow them to mix, eventually they will reach equilibrium. Until the point, again, at 3000 Kelvin, where you break the interactions, where the protons capture the electrons, the photons no longer interact with them, and so now they're allowed to evolve separately and follow different paths, and they no longer exchange energy because you removed their method of energy exchange. You remove the scatterings. So after the surface of last scattering, the photons now propagate freely, and they redshift as the universe expands, and the atoms remain and they cool off as well. They lose energy as well, but these populations are no longer in interaction. So these two populations used to be in equilibrium, and we know when at what temperature they stopped being at equilibrium, because that's the temperature at which atoms form and become stable. And we now see the remnant in photons, which now is microwave of this last temperature. The photons created way back when. Okay, so we now have kind of an image of the universe as it was almost 13.5 billion years ago, when it was very, very young and just becoming cold enough to form atoms. Before then, there were no stable atoms, right? So before that, we had this kind of green image of strong interactions and scatterings. And then on the right, we are where we still are today, where photons propagate freely between stable atoms. Okay. This is just an example of the history of the universe and this process of the universe. As you go back, it kind of heats, allowing for more processes to occurred many times. Or if you want to look at it in the reverse, from the Big Bang, the ambient temperature of the universe kept decreasing, and every so often it would pass a major step function or major step when it passed the ambient temperature relevant for a particular type of physical process, forever locking the universe in whatever the constituents were at that temperature and unable to change anymore. So in the beginning, we don't even know what the relevant quantum gravity processes were. We have here typical temperatures of 10 to the minus 44, time scales of 10 to the minus 44. That's the Planck scale. Energies of 10 to the 19 GeV. So the unification of gravity and quantum mechanics. As the universe cools, we start getting quarks and gluons and all these types of bosons and weak and strong interactions. As the universe cools even more, the gluons and quarks start combining into nucleons, like protons and neutrons, which before then were unstable, but at energies of about GeVs, you can start getting these stable nucleons. After that, we get separate nucleons and even nuclei, small nuclei, kind of banding together along with free-floating electrons and photons. Past the surface of last scattering of cosmic microwave background, we start getting stable atoms which means the photons now propagate freely in between these atoms. And then as the universe becomes colder and colder, these as well start to accumulate gravitationally and produce the first stars. The first galaxies, eventually leading to chemistry and biology and evolution and all that. So the history of the universe is governed by this process of expansion in space, which means the universe keeps becoming colder and thinner and colder, freezing processes at the last, as they were the last time it was hot enough to allow them to happen. And the further back you look in time, the hotter you look, the more energetic processes were allowed, and the more it kind of gets to probing higher and higher energy physics. The future, of course, is for the universe to keep expanding and get colder and colder. And it's a question of exactly how long that will last, and will something interesting else happen. But most interesting stuff is in the past. In studying nuclear physics or even interactions between elementary particles and quantum gravity, we're kind of probing backwards and backwards in time towards the Big Bang, which we still do not understand. Okay, this can also be represented in kind of these eras of the universe. Today, as I said, we're in the matter-dominated area. Before that, we were in the radiation-dominated era. You can see that the line for matter, which decreases like 8 to the -3, today is the highest one. Most density today in the universe is matter, but not so long ago, at a temperature of maybe about 10 to the 5 Kelvin, radiation was more prominent. So today radiation goes like 10 to the -4, it drops below the matter density, but in the radiation era, radiation dominated over matter. And before that, we had the lepton era, the hadron era, depending on which types of particles are stable at those temperatures. Going back in time means going up higher and higher in energy. Another example of something that we can measure today that's kind of a relic or an imprint of the early universe is the ratio between protons and neutrons in nature. Or because we don't find free neutrons, basically the ratios between hydrogen, which is protons, and helium, which is the most common place where we find neutrons in nature, inside nuclei of helium. So there's an energy gap or delta between the rest mass of a neutron and a proton. A neutron is slightly heavier. It's slightly heavier by about 1.3 mega electron volts. And if you want to convert that to with Boltzmann's constant into temperature, it's about 15 billion Kelvin. That means that when the universe was very, very young, notice this is about 1 to 3 seconds. So even long before cosmic microwave background separated, even further back, when the universe was just a second or two old, the universe was above this temperature of about 1 MeV, or about 15 billion Kelvin. The entire universe was that hot. That means that back then, there was thermal equilibrium between neutrons, electrons, positrons, and protons. So these processes could all go both ways. Neutrons could absorb positrons, creating protons and releasing antineutrinos, or a proton could absorb an electron and create a neutron and an electron neutrino. And a neutron could transfer directly, dissociate spontaneously to a proton and an electron and an antineutrino, and vice versa. The universe was dense and hot enough for all of these processes to happen together, which means that there must have been thermal equilibrium between the populations of neutrons and protons. What does thermal equilibrium mean in this case? It means that the ratio of neutrons, which are heavier, to protons has to obey a Boltzmann factor. It has to be exactly this Boltzmann ratio between the energy to the temperature, K Boltzmann T, e to the minus or exponent of the minus energy difference over the temperature. So we said that the temperature was about, the energy difference is about 1.5 10 to the 10 Kelvin. So we divided by the temperature measured in 10 to the 10 Kelvin, tens of billions of Kelvin. And obviously this ratio changes as the universe cools down because the temperature changes. But the equilibrium is maintained because these processes are very, very fast. It breaks when the universe becomes, for the first time, too cold for this interaction to proceed. That happens when the ambient temperature is about 0.8 mega electron volts, which is about the energy difference minus the energy of an electron. Because for this process of a neutron to dissociate into a proton and for this reverse process to happen, for a proton and electron to form a neutron, or for a proton to absorb an electron and form a neutron and a neutrino, the average energy must be enough for the sum of these energies, a proton and an electron, to be about the ambient temperature. You need enough energy to merge, to create the right side from the left side. This temperature is called TD, or T deuterium, because it's basically when, sorry, I'm not sure that's the deuterium one. We'll get to it in the next slide. But this temperature is approximately when you dissociate the neutron production from protons and electrons. So you freeze this at a temperature of 0.8, and if you put in the Boltzmann factor 1.5 divided by 0.8, you get about a factor of 1 to 5, about 20% or 1 to 5. That means schematically, if I look at every 48 nucleons at this freezing out point of neutron production, 1 in 5 will be for every 5 protons, we will have 1 neutron. So out of 48 nucleons, 8 will be neutrons and 40 will be protons. And that's it. At that point, spontaneous neutron production stops in the universe. But that's not the last thing that happens, because it's still, until 300 seconds, it's still too hot for neutrons and protons to merge together to form deuterium. Now, deuterium is an isotope of hydrogen, and it's rather stable. Much more stable than free neutrons, which are unstable. A free neutron will spontaneously decay with a typical lifetime of 880 seconds, or about 11 minutes. A spontaneous process of decaying to a proton, electron, and an antineutrino, because again, a neutron has high enough energy for that, and it's an unstable particle. What that means is that until 300 seconds, you have free neutrons floating around with protons, and they can't merge together because it's too hot to form stable deuterium. And if you have free neutrons, they're unstable, they will decay. This doesn't happen after 300 seconds because then the universe becomes cold enough to form stable deuterium. There are no longer free neutrons around, so neutrons stop decaying. So again, we have this kind of specific temperature of 8 times 10 to the 8 Kelvin at which stable deuterium forms, which is the endpoint for neutron decay. What does that mean? That gives us another Boltzmann factor. It tells us that at 300 seconds, for the 300 seconds that we had decay of neutrons, with a typical lifetime of 880 seconds, we had radioactive spontaneous decay of about 30% or 29% of the neutrons. So we can approximate that to be about 1 in 4. So out of our 8 neutrons, 2 of them decayed back to protons by the time deuterium formed, by the time the universe was cold enough to form deuterium. Which means out of the 48 nucleons we started the universe with, now 42 are protons and 6 are neutrons. these 6 neutrons, as the universe continues to cool down, will grab 6 protons from the environment, and together we have 12 nucleons, so we can form 3 helium-4 atoms, or helium-4 nuclei. The other 36 protons will just remain at 36 hydrogen nuclei, which means finally what this cosmological calculation gives us, this cooling down of the universe tells us, is that today we would expect for every 36 hydrogen atoms to find 3 helium atoms, or to have about 1 in 2, a ratio of 1 in 12. That gives us a number fraction of about 8% for helium, or a mass fraction of about 25%. And if you recall, when we discussed the structure of stars, the earliest stars, this was their composition. About, I think it was about 9% helium and about 21%, sorry, about, yeah, 9% in helium in mass, in number fraction, and about 29% in helium. So it's not a perfect calculation, but it definitely shows us how the building blocks, the foundations of building stars in the universe are themselves remnants of these calculations, which we do on the early physics and early nuclear physics right after the Big Bang. The first 300 seconds of the universe determined all the stars to be produced for billions of years after that. Okay, and people have done these similar calculations for more complicated networks of reactions. This is called BBN, Big Bang nucleosynthesis, and it basically gives the first elements, the first isotopes, basically up to about an atomic number of like something like 4 or 5. So hydrogen, helium, neutrons, protons, lithium, beryllium, nothing much after that. For the higher elements, as you know, we have to wait for stellar nuclear activity to produce them. But the first ones, the Big Bang nucleosynthesis, comes from these types of calculations. Okay, Yehu is on Miluim, so there's no tutorial today. He published a tutorial online. If you want, I can continue now for about 10 minutes to finish the final 2 topics of dark matter and dark energy, or we can take a break and for 10 minutes and do it at 3:05, and then finish the course with some dark matter and dark energy. Any preference?
I think maybe 5 minutes breaks, just fill up water. That's all.
Okay, any objections? Any other preferences? Short break. Okay, so 5-minute break, and I'll talk to you at 3. Okay, so we talked about the evolution of the universe, the different eras in the universe, how kind of the relativistic cosmology expands on Newtonian cosmology, and how the history and future of the universe are derived from the content in the universe, whether it's matter or radiation or vacuum energy. And we can't really finish a course in astronomy or a discussion of cosmology without saying that all of the matter and all of the radiation that we know of, that we study in quantum mechanics, that we study in school, that we see in our everyday lives, and that we see in astronomy and astrophysics, is today understood to be only a tiny fraction of what is actually the content of the universe. Less than about 5% of all the content in the universe today is expected to be what we call baryonic matter, or matter composed of baryons, of heavy combinations of quarks. So all the matter that we know in the standard model, if you want. And kind of realizing this was a shock and took a while. And it took a lot of disbelief and a lot of successive observations. And the way that we know this, because this is matter that we cannot observe directly, it emits no light, hence the name dark matter, and it participates in no interaction that we know of. is only indirect information gathered by observations of other things that we can see, mostly stars and gas. So Jan Oort, for a famous astronomer for whom the Oort cloud is named, already in 1932 noticed that the stars in our vicinity rotate too fast relative to the distance from the center of the galaxy. So recall the galaxy's existence was established in the 1920s following the Great Debate and Hubble's observations. And you can calculate from the amount of mass and Kepler's law how fast things should be rotating based on their distance from the center of the galaxy. And Oort noticed our stars around us rotating too fast. And what he did as a good scientist was to doubt his measurements and attribute it to a measurement error. He said that it can't be true. He probably made a mistake. A few years later, Horace Babcock also found a fast rotation, this time in a different technique. He analyzed the luminosity to mass relation for a galaxy. As you recall, when we talked about galaxies, different galaxy types have typical masses and luminosities, and from the relation of them, we can typically estimate the distance to the galaxy, the Tully-Fisher relation. So what Babcock did was see a discrepancy. He saw too little mass, or rather too little luminosity for too high mass as inferred from the rotation. And he attributed that as well to an error, or rather to a physical process. He said that there might be some light lost on the way, some extinction of light, some absorption. He thought that he was missing some of the light coming out of the galaxy, hence mistakenly thinking that the mass is less than it actually, that the luminosity is less than it actually is, and that would explain the mass, the high mass observed from rotation, or some other physical process, some dynamics in the arms that caused them to rotate faster. So he also found this discrepancy and didn't really believe it was true. Van den Hulst looked not at our own galaxy, he looked at M31, the Andromeda galaxy, and started plotting a rotation curve, seeing how the velocity of stars changes with the distance from the center of the galaxy. And he thought that there must be some mass outside of the stars that he could see shining to explain this fast rotation. In Keplerian terms, the mass causing this gravity for giving the energy for this rotation. Louis Wolders did a similar study for M33, another important galaxy, and also found it was spinning too fast. But all of these preliminary results were still very skeptical. They didn't quite go all the way and understand what they were seeing, in fact. The person who did understand what she was seeing was Vera Cooper-Rubin, pictured here on the right, famous astronomer, very important astronomer. She looked at rotation curves in the Milky Way from two separate sources. She looked both at stars and at neutral hydrogen clouds, so H1, neutral hydrogen, and plotted their velocities based on distance from the center of the Milky Way. What she found was this plot on the right. You can see distance to the galactic center at the bottom and the rotation velocity on the vertical axis. And what she observed was what's called flattening of the rotation curve. That is, the curve first goes very, very sharply up, starts to go down, but then flattens towards the right. And the sun is positioned here at 8 kilopascals from the center with a velocity of 220 kilometers per second. If you sum up all of the mass in the stars that you see, the mass in the stars and gas, you would have expected only 160 kilometers per second per hour sun. And you would have generally expected a decrease in the rotation curve going out. The visible matter, all of the mass of the sun, of the stars and clouds and gas that you can see, would only explain velocities going down towards the right. And this difference, she explained, was due to more mass than we can see. And that mass has been called dark mass. So this is the Milky Way. On the right, you have a similar plot for M33. And again, you see the observations from both stars in yellow and from hydrogen clouds, 21 centimeter hydrogen lines in blue, again show that this curve is not dipping down, while the visible disk, the visual mass that we see, should have provided a decreasing curve of rotation. Why does this happen? Well, Kepler's law, gm equals omega squared r cubed. If you want to calculate the velocity is omega r. So that's r times omega, or the square root of gm over r cubed. And so if you plot what type of mass distribution you have, you will get different types of behaviors far away. For example, if you're looking outside of a bulk of mass, or if you assume most of the mass is in some center, some bulk, then you can just assume outside of some radius, the mass is constant. And then the velocity will decrease like 1 over square root of r. If you assume a sphere, kind of the opposite case, an infinite sphere with constant density, then you find that the mass grows like r cubed. And because gm over r cubed will then be constant, you'll find that the velocity grows linearly with r. A disk is kind of an intermediate case. We expected most galaxies to behave like that. If the disk has some planar distribution, sigma times r squared, then you'd expect the velocity to grow like r to the 1/2. Now, what we would have expected looking at the Milky Way or Andromeda or other galaxies is a lot of mass in the center, and then kind of decreasing outwards where we see that there's less and less mass. It's not uniform, it's decreasing. And so we would have expected behavior somewhere between this maybe r to the -1/2, or maybe around r to the -1/2 or slightly above that. We would have expected a decrease outside of the visible matter at least. What we in fact see is that it levels out. In the Milky Way, it even keeps growing for M33. So there is more and more mass outside of the stars that we see. And that's the dark matter. And since then, it's been observed almost in every galaxy where we looked for it. And we now expect the dark matter halo to kind of surround the galaxy much farther away than the star that we can actually see. Today, we think that in the cosmological process of creating galaxies, what actually happens is that it's the dark matter that starts clumping or creating overdensities, and then the baryonic matter, the gas, flows to the potential wells created by the dark matter, seeding and creating galaxies in the dark matter overdensities. So dark matter is really what drives most of the mass in the universe is dark matter. And wherever it accumulates, the galaxies will fall in and create themselves over there. However, as I said, in the last 20 or 30 years, we have a new form of constituent in the universe, and that's dark energy. Because all these measurements trying to see how fast the universe was slowing down and to determine whether it's subcritical or supercritical, as we discussed earlier, to tell what the future of the universe would be, found that the universe was actually reaccelerating rather than deaccelerating. And that can be explained by the universe being vacuum dominated or cosmological constant dominated. So whenever the universe is expanding, there's more and more vacuum. There's no more matter, no more radiation, but there's more vacuum. And if that vacuum has some cosmological density, cosmological constant density, then that will be the thing driving further expansion and faster expansion. And that's what we think we are seeing today, an accelerating expansion of the universe after a period of slowing down. and we don't know exactly, but we think this will cause the universe to eventually expand and expand forever, at least on a cosmological scale. In terms of the critical density or relative densities, we see that today we think about 3/4 of the universe is actually dark energy, with about 1/5 or slightly over 1/5 dark matter. And very, very little, about 4% of the universe is in fact what we know to be regular matter, baryonic matter, mostly intergalactic gas. Some of it, about 0.5%, 1 in 200 parts of the universe are actually stars and gas. So everything that we see is a tiny fraction of what there is to understand about the universe. We don't really understand neither dark matter nor dark energy. Showed here on the right are kind of different measurements of the different densities of the universe relative to the critical density. So we have here omega matter and omega lambda, which is the dark matter, the dark energy component. And we see that all the measurements kind of agree that the universe is almost flat. It's almost at that marginal point between supercritical and subcritical to a very good accuracy. We're still trying to refine these measurements and understand just exactly what the relative percentages of different types of matter, radiation, and energy are in the universe, because that will determine the ultimate fate of the universe, whether it will expand or collapse, or what will happen to it and to us. All of these are open questions, and as we said, even the Hubble constant does not have an agreed value today. So cosmology is still a very, very active field of research in observations and theory. And that completes our course. Yehu uploaded a tutorial PDF and a homework exercise number 14 to the website, to the Moodle. The exam is in 1 month, August 1st. So I think it's probably one of your last exams, the 1st of August. It will be a home exam. Basically, you have until then to submit the homeworks. I think we said 80% of 14, which is 11 point something. So we'll mark it down to 11 homework exercises. If you submit more, it will be the best 11 out of 14. I'm available for questions if anyone has them over the summer. And I hope you enjoyed the course and learned a lot and find the topics interesting for future study. And you're welcome to try and talk to me or Asaf, the other astrophysicist, or Ma'ayan, who's the new faculty joining in astrophysics. And have a great summer. Good luck. You're welcome.
וגם מזל טוב אגב.